Howdy, my name is Carrie Jones, and this is my final summer presentation on the partial thermal cycling of nickel titanium hafnium shape memory alloys. This summer, I have worked with Alexander Dimblon and Dr. Ibrahim Karaman. So what are these shape memory alloys? They are a type of metallic alloy that has multiple different solid phases that are transitioned between when heat and stress are applied to the material. So this video here shows kind of how that works. The shape memory alloy, or SMA, starts in the twinned martensite phase, and then it's deformed to the detwinned martensite phase. When it's heated back up in this warm water, it transitions to the austenite phase and goes back to its original shape. This ability for the material to kind of remember its shape allows it to be used for many applications. So how are we using them? The project I'm working on is the NASA University Leadership Initiative project, which ultimately has the goal of creating supersonic passenger aircraft. The biggest problem with supersonic aircraft is their sonic boom that can cause damage to surrounding areas if it's too loud. So on the materials side of this project, we're trying to fix this problem by using shape memory alloys as actuators to create sort of a bump on the outside of the aircraft. So this will work to reduce that sonic boom noise when the airplane goes into supersonic flight. For these actuators to be used in this particular application, they need to be able to be used up to 100,000 times or 100,000 cycles. So with the current methods that we're using to cycle these materials, we're only able to achieve about 3,000 cycles, which is pretty far from that 100,000 cycle goal. So if we use another method of thermal cycling called partial cycling, we can dramatically increase this fatigue life. So if we do a 90% partial transformation, we can extend the fatigue life to around 7,000 cycles. And with a 75% partial transformation, we can achieve over 16,000 cycles, which is over 5 times the fatigue life that we can get with no partial cycling. Partial cycling is different from full thermal cycling because the material is not fully transformed between the austenite and martensite phases. Here we can see that this full thermal cycle that goes all the way from one phase to another and back, and a partial cycle that only undergoes part of that transformation. So by doing less of a transformation in each cycle, we're able to increase the total number of cycles that we can get out of the material and ultimately extend that fatigue life. There isn't much literature out there on partial cycling of shape memory alloys, but from the 11 papers I found in my literature review, there were 4 of them that included actuation fatigue studies like the ones that we're doing. The other ones all mostly focused on differential scanning calorimetry or some other type of analysis. And of all those papers I looked through, most also focused on nickel titanium, even though there were a few that analyzed other materials like nickel titanium copper. But none of these partial cycling papers that I found studied nickel titanium hafnium, which was the material chosen for the NASA ULI project. So this shows how important it is that we study the actuation fatigue of this material, since there's hardly any literature in this area. So what methods are we using to study these nickel titanium hafnium shape memory alloys? The primary methods we're using include differential scanning calorimetry, digital image correlation to look at localized strain during fatigue tests, other fatigue test data, and micro CT imaging. So focusing on that fatigue test data, this summer I worked in collaboration with Dr. Karakallis and Matthew Kuhner to develop some tools to analyze the evolution of transformation temperatures throughout the fatigue life of these shape memory alloys. The tool that I focused on developing was a MATLAB code that calculates the 4 transformation temperatures for every thermal cycle throughout a fatigue test. As I showed you earlier in one of these slides, these tests can last thousands of cycles, so it could take me months or even years to calculate all of those transformation temperatures by hand. So this MATLAB code has been a great new tool for us to have, so I don't have to do that. Once the code was up and running, I was able to put some real fatigue data in and see what the transformation temperatures looked like. Here, you can see the evolution of the austenite start and finish transformation temperatures, and those are the temperatures where the material starts and ends the transformation to the austenite phase during the heating part of a thermal cycle. And you can also see the martensite start and finish temperatures, which are the temperatures at the beginning and end of the transformation to the martensite phase. So that's during the cooling part of a thermal cycle. So all these transformation temperatures change over time, as you can see in this plot, and some of them change a bit more dramatically than others. We can also throw partial cycling into the mix. Here we have 2 partial cycling tests along with that full cycle test. So on the left is the full cycle test, the middle and right are the partial cycle tests. So one of those tests, the one in the middle, stays on the lower temperature end of thermal cycling, and the one on the right stays on the higher temperature end. Those are different heating control methods, but both have the same amount of partial transformation. Both of them have a 75% partial transformation. So these temperatures here, circled in blue, follow similar trends, and these other temperatures here, circled in maroon, also follow similar trends, but those are slightly different than the blue trends. It kind of looks like these maroon ones change a bit more than the blue transformation temperatures. So these relationships will all be helpful in developing a theory for the micromechanical mechanisms behind partial cycling. And that brings me to the next steps in our project. The first is to develop that partial cycling theory. This will be done through continuing these analysis methods and kind of linking together trends from different methods. So, for example, linking together this transformation temperature evolution with these digital image correlation images. So in the DIC images, we can see that some samples have very localized strain, while some have strain more evenly distributed throughout the sample. And these are all important things to consider as we develop a theory, and in the discovery process, we may find that we need to run a couple more tests to complete our study. Then finally, after all of that is done, we will hopefully have what we need to publish a journal paper on partial cycling with nickel titanium hafnium. This concludes my final presentation. Thank you all so much for watching, and a special thank you to the OREU program and all of my mentors and collaborators who made this summer possible.